Hi class, today we are going further into R2 and R3 by looking at algebraic vectors in both R2 and R3. So algebraic vectors are those which are represented on the coordinate plane. So they allow us some more flexibility in what we are able to do with them in many applications further on. And we can use vectors for more things than just what you might typically think of when we get into chapters 8 and 9. So this is a long note, so I'm going to break it into 2 videos just to kind of allow your brain to wrap its head around your brain. Well, you know what I mean, just to allow your brain to kind of give some time in between so it's not just one long continuous video. So you can take the opportunity to copy down what I have here and then just kind of follow along. Or it's up to you, however you learn best through these videos. Okay, so what we're going to do here is define a vector OP in terms of the unit vectors. So OP is a position vector. So you can see here on my diagram, what I'm attempting to do is draw a vector from the origin out to point P. So in this case, point P is ABC. So I will draw that resultant vector there in red. Okay. Now I drew the coordinate box to give you an idea of where everything is. Okay. Now OP in 2 space can be written with unit vectors I and j. So perhaps we can go down here to 2 space to understand this first. Okay, so if you have any vector OP, so here's your O, and then here's your P, and it can be just drawn like this. Okay, and we'll say that this is AB. Well, that means that this distance here is A, and this distance here is B, which corresponds, if you create a box, to this distance here, which is also B. Now, unit vectors are vectors that are only one long. So we could talk about the unit vector I as being a vector that is 1 unit long and on the x-axis. So that means that this whole distance here is A times I, okay? Because I represents a unit vector that's 1 long along the x-axis, and then you multiply it by A to get its length, to get its magnitude. Similarly, J is a unit vector in the y-axis direction. So this whole distance from here to here is represented by B vector J because it is in the direction of J, and then whatever B is, B long. So in R2, this vector OP can be written as coordinate AB. But AB can be written as OA plus OB, okay, where A would be this coordinate here, and B would be this coordinate here. Now, OA can be written as AI plus BJ. So any position vector OP can be written as a sum of 2 scalar multiples of the unit vectors. Okay, so if we go back up to R3 here, so it says OP can be written with unit vectors I and j. That's what I just did. Now OP ABC, so in 3 space, can be written with unit vectors I, j, and k. So I, again, lies in the x direction and is 1 long. So that is I right there. I'll use different colors here. And then j is in the y direction and 1 unit long. And then k is in the z direction and 1 unit long. Okay, so this is talking about R2 and this is talking about R3. Okay, so all of these vectors I, j, and k have magnitude 1 and lie on the positive x, y, and then z axes respectively. So OA can be defined as just wherever A ends up. OB can be defined as here, wherever B ends up. And OC is wherever C ends up. And so in R3, OP can be written as an addition of these three, okay? So in this case, OP, which is ABC, sorry, there's no vector on that, I didn't mean that. So this can be written as AI plus BJ plus CK. Okay, so it's this vector plus this vector and then plus this vector. Okay? All right. So, for example, if you have OP equals negative 3 times 8, sorry, not negative 3 times 8, negative 3, 8, then this can be written as, it can also be written as minus 3 times the unit vector I plus 8 times the unit vector j. Okay, because if you draw it, minus 3, 8, okay, there's your OP, and here's your I, and here's your j. So you're multiplying your I by negative 3 to get this resultant here, and then you're multiplying your j by 8 to get that vector there, and then the addition of them is your vector OP. Okay, so just for your reference, this is called coordinate form. And this is just called writing it with unit vectors. So if a textbook asks you to take it from unit vectors to coordinate form or coordinate form to unit vectors, that's what they're talking about. So let's summarize in this box here. Every vector in R2 can be written uniquely in terms of I and j. The position vector can be represented as OP equals AB or as OP equals AI plus BJ, where O is the origin. So in R3, it can be written with I, J, and K, where the position vector is ABC, or AI plus BJ plus CK. Okay, so I, again, it's 1 long and then right on the x-axis, so it would terminate at 1, 0, 0. J is 1 unit length on the y-axis, so it would terminate at 0, 1, 0. And K is 1 unit long along the z-axis, it would terminate at 0, 0, 1. So if you have position vectors OP, okay, how do you write that using unit vectors? So it's AI. So the A here is 1, so you can just write I plus BJ. So B is 2, 2J. It's as simple as that. OQ, its A value is negative 3, so negative 3I. And now it would be plus 0J, so you can just leave it like that. Okay, alternatively, it can give it to you with a unit vector. So this A value is negative 1, and the B value is 5. So this is referring to the coordinate negative 1, 5. This one you'll notice there's no value of I, which means that the A value must be 0, and the B value is negative 1, the coefficient in front of J. So this is referring to the position vector with its head at 0, negative 1. Okay, so we can also talk about vector addition in component form, okay? So I'm going to draw this diagram, and hopefully that will help you with your understanding of what's going on here. So we're going to put our origin there, and we're going to create a vector OA, which you can draw up here. And its coordinates are going to be A, B. And then we're going to draw a vector D, which will terminate over here. And then we're going to call its coordinates C, D. So if we want to come up with the sum of this vector, we can draw our parallelogram. So here's our resultant. So the question is, what are the coordinates of this resultant? Well, we're going to show over here that all you have to do is add the two x values together and add the two y values together, and then you get your resultant. So vector addition in component form. So if you're adding vectors, then you just have to add the x's to get the resultant x and add the y's to get the resultant y. So we're going to show why this is true using unit vectors. So because OA can be written as AI plus BJ, and OD can be rewritten as CI plus DJ. Okay, so these are just taking our coordinate form and rewriting each with unit vectors. So now if you take OA plus OD, you could really take AI plus BJ plus CI plus DJ. Okay, now we learned in our properties yesterday that adding vectors is commutative. So I can move AI and CI next to each other using the commutative property, and BJ and DJ can be next to each other, again, using the that property. Okay, so now we can collect like terms. So A plus C can be the coefficient on our I vector, and B plus J can be the coefficient on our J vector. So if you rewrite this then in terms of just your components, you get A plus C as the X value, because that's the coefficient in front of I. That's what you're multiplying this unit vector by, so that's how long it will be. And your Y value will be B. Sorry, that shouldn't be B, that should be D. B plus D. Okay, so this is the mini little proof that the resultant vector OA plus OD, you just add the X values or add the Y values. Okay, so therefore to determine the sum of two unit vectors in component form, you add corresponding. Okay, subtraction is basically the same. So if you had OA minus OD, you would have AB minus CD. So you would just have A minus C, B minus D, and then end. Okay, so if you need to like see an example of what I mean like this, basically I'm saying if you have the vector OA is 2, 3, and you're adding it to the vector OD, which is like, I don't know, 5, 1, then OA plus OD would be 2 plus 5 is 7, 3 plus 1 is 4. So this is the resultant vector of the sum of these two vectors. And you can draw it out to see how that looks. Now we're going to do a similar proof in R3 using something called a parallelepiped. So get ready. This is fun. I'm just seeing how much we got there. Okay, so oh man, I really hope I can draw this with this trackpad, even if it gets a little touch and go for me. I'll try to use colors. Okay, so we are going to use a parallelepiped. So you're like, Mrs. Weens, what is this? Okay, we're going to create 3 vectors. So OB is going to be here. Okay, so that's OB. So here we're talking about vector OB, and we're going to give it the coordinates P, Q, S. Okay, and you might want to get another color. Actually, I'll do purple. And we're going to put C kind of over here. Could be anywhere, but I'm just trying to make it so it's not too cluttered. So we're going to call that C, and its coordinates are M and R. And then we're going to have a third vector kind of coming out at you here. What do I want? We'll call it D. Okay, and its coordinates are F, G, H. Now we might have to write over this later, but Okay, so here we have OB. So this is the coordinate form of OB. Here is the unit vector form of OB. Here's OC and OD. So understand this first before we even draw the parallelepiped. So these are just three different vectors in three space. And we're going to draw a parallelepiped based on them. So I'm going to kind of just use a basic color for everything that's not those. Okay, so from B, you want to draw a vector that's parallel and equal to OD. Here, this is O. Okay, and then connect the box at the top like this. Okay, and then parallel to B, you want to create the same line here. It's kind of like the bottom. And then parallel to C, you want to create the same line there. That's the top. Okay, and then parallel to P, you want to create that. And then these two can be connected. Oh no, I didn't mean to do that. Ooh, erase. Okay, phew. Sorry, don't connect those two. Connect these two. Okay. We call this point P up here, by the way. So connect these here. And then you can do one parallel here. And then connect that. And then connect this. Okay, so that is your parallelepiped. It's basically like a parallel angle rectangular prism. And we are going to draw in red here the resultant from O to P. So O cuts from the origin diagonally through the parallelepiped. Okay, so and then we'll call this point down here Q. That's important. I'll do a different color. So this down here is Q. So draw also a dotted line from O to Q. Okay, because notice OQ plus QP gives you OP. Okay, so notice that OP can be written as OQ plus OD. Okay, using either the parallelogram law or you can use the fact that OD is equal to QP. So OP can be written as OQ plus OD. Okay, make sure you get that first because we're getting a little weirder after this. Okay, but notice that OQ can be written as OB plus OC. Okay, OB plus OC is equal to OQ. So OP can be rewritten as OB plus OC plus OD. So now, basically from here, we can rewrite each of these with their unit vector definitions. Then we're just going to collect like terms, and you'll see that basically you're just adding the three coefficients together. Okay, so for here, you get your PI plus QJ plus SK, and then OC, you get your MI plus NJ plus RK, and then for OD, you get your FI plus GJ plus HK. Okay, so if you collect like terms on I, you get P plus M plus F all in front of I. And then you get, sorry, that should be plus. And then you get Q plus N plus G all in front of your J. And then you get S plus R plus H all in front of your K. So then if you put this to coordinate form, your X value is just adding those three X values together. Your Y value is just adding the three Y values together. And your Z value is just adding the three Z values together. Okay, so when adding or subtracting vectors in R3, you just add or subtract their respective components. So if you want OA minus OB, okay, so if you have A1, A2, A3 as your first coordinate, and you're subtracting B1, B2, B3 as your second coordinate, then your resultant would be you just take A1 minus B1, A2 minus B2, and A3 minus B3. Okay? So a lot of visual proofs to kind of show something that might seem obvious to you, but that's part of, university level mathematics. Okay, then we have scalar multiplication, just so you know. So if you have a scalar multiple outside of a position vector, then that scalar multiple can just be written in front of the coordinates and distributed through. So the same thing is true in R3. Okay, so we're just doing the same set of what's up there, just adding the third coordinate, C. So this M is a scalar, and we can just put it through. So basically, it's just saying that you can distribute it through the components. Okay, so therefore, to multiply an algebraic vector by a scalar, each component is multiplied by that scalar. Okay, so let's just do this example, and then hopefully that clarifies it, and this will be the end of video 1. Okay. So given OA is 1, 3. So here, let's put some. Oh, here we need another one. Okay, actually, that was not good. Let me make those a little more even. I just didn't know we had to go up to 4. Hopefully you're doing a much better job than I am. Okay, I'm sure you're doing awesome. Okay, our first vector OA is 1, 3. So you go over 1, up 3. There's A. So here's our vector OA. 1, 3. Okay, and then we have our vector OB. So OB is at 1, 2, 3, 4, and then negative 2. So there's OB. Okay, so determine the components of A plus B. So A plus B is just equal to 1, 3 plus 4, negative 2. So literally you just take 1 plus 4 as the x values, and then 3 minus 2 as the y values, and you get 5, 1. So if you draw it, it should look right as the resultant. So 1, 2, 3, 4, okay, 5, and 1. So that looks right, okay? If we were to draw a parallelogram, that is where the corner would end up. So this is A plus B, which is 5, 1. Okay, now if we're going to do A minus B, what would that look like? So A minus B then is 1, 3 minus 4, 2. So it's 1 minus 4, which is negative 3, and 3 minus a negative 2, which is positive 5. So it would be negative 3, and then up 5, so about there. So why does that make sense? Well, if we'd had negative B, then negative B would be going in this direction. And so this is the resultant of A plus negative B, okay? And that's why you get A minus B up here. Okay, so visually that should make sense. Okay, then finally it asks for 2 of A plus B. So that's just 2 times, well, we already found that A plus B is 5, 1. So that would be 10, 2. So again, we'd be going over 10 up 2. It would just be this vector in the same direction, but it would be double the magnitude. Okay, so that is video 1, just some basic stuff. Really the results of it aren't too complicated. You're just adding and subtracting subsequent x and y values. It's just the proofs that might take a little while to wrap your head around. So just take a little break and then move on to the next series. We're talking about vectors defined by 2 points. Thanks for watching, guys. Hope you learned lots and you're going to learn more.